Okay, so at the end of the last video, we talked about the difference between random error and systematic error. So take a look at this question. This is from an IB exam question from the past couple years. And it says the diagram shows an analog meter. Notice the British spelling of analog, by the way. An analog meter with a mirror behind the pointer. What is the main purpose of the mirror? Okay, so the answer choices say to provide extra light when reading the scale, to reduce the risk of parallax error when reading the scale, to enable the pointer to be seen from different angles, or to magnify the image of the pointer. Okay, so see if you can figure out the answer to this question. Okay, so the answer to this question is B. Okay, to reduce the risk of parallax error when reading the scale. So mirrors by themselves don't produce extra light. C says to enable the pointer to be seen from different angles, but you don't want that because if you are viewing something from different angles, that would actually introduce parallax error, which is a type of random error. Okay, so it's not C. And D, to magnify the image of a pointer, a plane mirror like that would not make the image bigger. Now, what you want to do with the mirror is to reduce the risk of parallax error, because if there is a mirror behind the pointer, then it becomes very, very obvious if you're viewing it at an angle. You can see in the mirror, you can see a reflection. If you're viewing it straight on, you shouldn't be able to see any reflection at all because the image of the needle is going to be right behind the actual needle. Whereas if you're viewing this measuring device at an angle and there's a mirror behind it, then you can kind of see the reflection in the mirror behind the actual measuring device. Okay, so the answer there is B. Okay, so you should have learned in past science classes about accuracy and precision. And so hopefully this is a review of information you've seen before. But when you are collecting a series of data, you can talk about the accuracy and precision of your data points. And when we refer to accuracy of a set of data points, what we're talking about is how close the data points are to the true or accepted value. When we talk about precision of data points, we're talking about how close the data points are to each other. Okay, so make sure you add those definitions to your notes. But again, these are things that you should have learned in your past science classes. Okay, so just to put that in a different frame, if you have repeated measurements and they're always very, very close together, then you could say they are precise. In other words, by saying they're precise, you could say they have a small random error. Okay, because there's not a lot of spread between the data points. Remember, random error is just as likely to be too high as it is to be too low. Okay, and so if you have data that is precise, that means you have data very close to each other. That means you don't have a lot of random error. All right, now again, there's a difference between precision and accuracy. If you have repeated measurements that are pretty close to the true value, that means they're accurate. That means the systematic error is small. Okay, however, they might not necessarily be precise. Okay, so here we can see using the analogy of a target where the center is the true or accepted value, we can see, accurate and not precise, or precise but inaccurate. Okay, here the data is precise because it's pretty grouped close together, but they're all kind of offset. Notice how they're all offset from the center of the circle. Okay, so this would be, this on the right would be an indication of a systematic error, shifting all the data away from the true or accepted value. And on the left, this would be an example of a random error, where all the data points tend to be around the true or accepted value, but they're kind of spread about. Okay, so in other words, precision has to do with random error and accuracy has to do with systematic error. And these analogies you've probably seen before. They're all pretty similar. Here you can see the different possibilities. Again, in the analogy we're talking about, the target, the center of the target is the true or accepted value, and the x's are the data points you're taking. Okay, so you could have data that's very accurate and precise. You could have inaccurate data with a systematic error. Okay, either precise and inaccurate, or just all over the place, imprecise and inaccurate. Okay, that's obviously the worst case scenario. Or you could have data that's accurate, where when you average it together, it tends to be about the true value, but they're all kind of scattered about. Okay, so let's just take a look at one more question having to do with accuracy and precision. I don't want to spend a lot of time on this because I've discovered that most students taking IB physics are pretty familiar with precision and accuracy by the time they get to this level. So let's just take a quick example. Okay, an ammeter has a 0 offset error. Now, do I expect you to know what an ammeter is right now? No. Okay, so for right now, let's just say some type of measuring device. Next year in IB Physics 2, you'll learn that an ammeter is actually a device used to measure electrical current, but that's not important right now. 0 offset error is a type of error that you should be familiar with because we talked about this before. This tends to lead to systematic errors. Okay, we talked about that in the last video with the bathroom scale. This fault will affect what? Okay, so there's two parts to this question, and again, this is from past IB exam, and so this is the level of question you might be expected to see. Number one, you have to know what a 0 offset error is, and that it's a type of systematic error. And number two, you need to know that systematic errors tend to affect not the precision necessarily, but the accuracy. Okay, so the answer here should be C. Now, is it possible there's also issues with the precision? Yeah, of course. Okay, but probably not caused by the 0 offset error because that is just a systematic error. Precision would have to do more with the random errors that you might see. Okay, so pause there if you need to take a look at that some more. Okay, so please make sure that you are familiar with the difference between accuracy and precision, and that you can explain the difference between those two and what they have to do with random error versus systematic error. Okay, so we are going to move on, and we are now going to talk about the different types of uncertainty. Now, up until this point, we've been talking about uncertainty, and mainly we've been talking about what's called absolute uncertainty. Okay, so absolute uncertainty is also called raw uncertainty in a measurement. And the key to absolute uncertainty is absolute uncertainty has a unit with it. Okay, so if I say plus or minus 1 centimeter or plus or minus 0.5 degrees, that is an absolute uncertainty. Okay, also called raw uncertainty. So for example, a student measures the length of a line with a 1 meter stick to be 11 millimeters plus or minus 1 millimeter. What is her absolute uncertainty? Well, it's right there. And I know right away that's the absolute uncertainty because it has a unit with it. Okay. By the way, I could also write that as 11 plus or minus 1. And I could use parentheses and put millimeters on the outside. That is just as good as writing it like this. It doesn't matter which one you do, but you might see it either way. Okay, so this is what's called absolute uncertainty. I know on the slide it says absolute error, but we're going to call it absolute uncertainty. I don't like error in this connotation because it makes it seem like you're making a mistake, and we've already established that uncertainty just arises because of imperfections in measuring techniques, okay, and the requirement that you make estimations in situations. Okay, so that is absolute uncertainty. Okay, so pause it there if you need to add that to your notes. Absolute uncertainty, same unit as what it is you're trying to measure. Okay, so I'm going to erase this. And now let's talk about fractional uncertainty. Okay, on the slide it says fractional error. I'm always going to call this fractional uncertainty. To be honest, I'm not going to use fractional uncertainty very often because I find it very difficult to explain to people what it actually is. But basically, the way you calculate fractional uncertainty is you take, again, I'm going to cross the word error and put uncertainty, okay. So the fractional uncertainty would be the absolute uncertainty divided by the measured value. And you would leave that as a fraction or as a decimal. So for example, if I write down the length of a line is 11 millimeters plus or minus 1 millimeter, that is written in absolute uncertainty. Okay, to make it fractional uncertainty, I would write down 11 millimeters plus or minus, and I would do the measured value, or the absolute uncertainty divided by the measured value. This is my absolute uncertainty. This is my measured value. So I would write down 1 over 11, which is 11 millimeters plus or minus 0.09. Okay, now I don't particularly like that because then I have people ask me 0.09 what? It's not a percent, it's a fraction. And so I don't really like that. You do need to be aware of what fractional uncertainty is, just in case you ever see a question about it, but that's not something you're going to see a lot from me. Typically, I deal with uncertainties only in the absolute form or in the percent form. Okay, so there's 3 types of uncertainties. You'll see absolute, fractional, and percent, and it's very uncommon to see fractional, at least from me. You might possibly see it on the IB exam, but usually you'll be working with either absolute or percent. Okay, so let's talk about percent uncertainty. Okay, the way you calculate percent uncertainty is very similar to the way you calculate fractional uncertainty, except that you multiply by 100 to make it into a percent. Okay, so for example, in the last example, I had 11 millimeters plus or minus 1 millimeter. That is written with absolute uncertainty. I can change it to percent uncertainty, and by the way, pay close attention because this is something you're going to have to do a lot. I'm going to do the absolute uncertainty divided by the measured value, just like we did with fractional, and then I'm going to multiply by 100 to make it a percent. And if I do that, I'm going to get 11 millimeters plus or minus 9%. Okay, and so this is a percent uncertainty. This is saying my measured value is 11 millimeters, but I could be higher or lower by 9%. Now, 9% of what? 9% of 11 millimeters. Okay, so I much prefer to work with percent uncertainty compared to fractional uncertainty because 9% kind of makes more sense in my mind. Okay, I know exactly what that 9 represents. I know what that 9 represents. It represents 9% of my measured value, which in this case is 11 millimeters. Okay, so pause there if you need to take a look at that. And then just take a look at some practice. Okay, we're not going to go through all of these because these calculations are all pretty basic calculations. Okay, but you should be able to convert very seamlessly between absolute uncertainty and percent uncertainty. Okay, so you can see both ways right here. The way you would convert from absolute to percent is you would do, for example, for this one, you would write down 13.1 plus or minus 0.6 divided by 13.1 times 100, and then that would get you, wow, you can't even see it because this background is so dark, but it would get you 5%. Okay, now let's say, hypothetically speaking, you want to convert from percent back to absolute. Well, we'll talk about that here in just a moment. Actually, I can give you an example right now of that. So let me open up a new slide and change the background. Actually, I'll do it over here. Okay, so hypothetically speaking, let's say I had 13.6 plus or minus 5%, and I want to convert from percent to absolute. Okay, so what you would do is you want to figure out, okay, so it's plus or minus 5%, and it's 5% of this number. So first, you need to convert that percent back to a decimal. So you would do 5 divided by 100. Okay, that turns 5% back to decimal, and then you would multiply by the measured value. Okay, so in my calculator, I'm going to type in 5 divided by 100 multiplied by 13.6. And I get a value of 0.68. Okay, so 13.6 plus or minus 0.68, and that's how you would go from percent back to absolute uncertainty. Now, as we'll see later, there's rules for dealing with uncertainty, and one of the rules is that when you are talking about absolute uncertainty, you have to have the same number of decimal places as you do in your measured value. Okay, and so I would not leave this as my final answer. I would actually round, because I have one decimal place right here, I would round my uncertainty to only have one decimal place. And so I would write that plus or minus 0.7, and that would be my answer. Okay, so that's how you would go from percent backwards to absolute. Okay, so make sure you're familiar with going both ways, from absolute to percent and from percent back to absolute. Okay, now the very last thing I want to talk about in this video is what do you do when you have a set of data and you have to take an average of a set of data. Well, we know that we've talked about uncertainties in individual measurements, okay, but what if you have a set of data and you want to know the average value and its uncertainty? Okay, so for example, let's say you're measuring the time it takes a toy car to roll down a ramp, and you do the experiment, let's say 5 times, and you get 5 different values. Okay, now each of these individual times has an uncertainty in it, probably because of the measuring device, probably because of human reaction times, whatever. Okay, the average value though has its own uncertainty. Okay, and so what we're going to talk about now has a name, and this name is called the half-range method. And the half-range method applies only when you're averaging a set of data. Okay, so the half-range method is a way to determine the uncertainty in a set of data of the average value. Okay, so here is how the half-range method works. Okay, what you do is you take the range. Now, what does that mean, the range? That means the highest value minus the lowest value. Okay, now this is called the half-range method. So if this is the range, you would take half of that value. Okay, and that gives you the uncertainty in your average value. Okay, so just to go back to the rolling a car down a ramp example, pause it there if you need to write that down, by the way, that's important. Okay, but just to go back to this example, we have 5 different times here, and if we average these 5 different times, we get 8.12 seconds. Okay, to find the uncertainty in that average value, we apply the half-range method. We take the highest value, which is 8.16, minus the lowest value, which is 8.08. Okay, the range is 0.08. And so half of the range is plus or minus 0.04. And so that means that what I would write down for the average is I would write down 8.12 plus or minus 0.04 seconds. Okay. Notice, by the way, that when I write down 8.12 plus or minus 0.04 seconds, what I'm saying is that the actual value is somewhere between 8.08, okay, that's if I subtract 0.04, and 8.16, which is what I would get if I added 8.12 to 0.04. Okay, so is that consistent with my data? Are all of my data points between those two numbers? Yes. Okay, and so the half-range method allows you to find the uncertainty in an average value. Okay, so we've talked about how to find the uncertainty or how to choose a reasonable uncertainty for individual measurements, but this is how you'd find the uncertainty for an average value. Okay, which you do all the time in science because you're always trying to average values to reduce the random error in your experiment. Okay, so example, this is an IB question. A student measures a distance several times. The readings lie between 49.8 centimeters and 50.2 centimeters. This measurement is best recorded as what? Okay, so again, if we have a range of data, okay, number one, we want to find the average. The average between these two values is going to be right in the middle. That's 50.0 centimeters. Plus or minus, the uncertainty is going to be half of the range. So 50.2 minus 49.8 is 0.4. And then if you take half of that, you get plus or minus 0.2 centimeters. Okay, and so this is how you would record the average value, okay, using the half range method. All right, and just to clarify, we've talked about two types of uncertainties. We talked about uncertainties from individual measuring devices for individual measurements, and what we just now talked about was the uncertainty in the average of a data set for multiple measurements or multiple trials. Okay, what you would typically do if you were writing like a lab report, or if you're writing your IA, or if you were doing an experiment, is you would take the two uncertainties, and whichever was the bigger of the two, you would basically use that uncertainty. Okay, but those are two types of uncertainties we talked about in the beginning. Of the last two videos, we talked about the uncertainty in individual measuring devices and how to make those estimations and how to make sure that they're reasonable. And what we just now talked about was the uncertainty in the average of a data set, okay, using the half range method. So make sure you're familiar with the half range method. Okay, so in the last video, we will talk about doing uncertainty calculations. That's probably one of the more challenging parts of this unit. Okay, so please make sure that you're prepared for the next video. As always, let me know if you have any questions, and I will see you guys in the next video.